Welcome to video 58 in our series on tensor calculus. In this video, we're going to develop the concept of the tangent space. The tangent space is going to be the framework we need to analyze vectors and tensors relative to our surface coordinates. Here I've drawn a surface with a point P, and from the last video we know that the surface is a two-dimensional submanifold embedded in a three-dimensional Euclidean space. So, being that it's two-dimensional, we'll need a two-dimensional coordinate system to analyze the points on the surface. So we'll introduce what we call surface coordinates. Our surface coordinates are labeled with the letters S, S1, and S2 as you see here. And we do that to distinguish them from the coordinates of the ambient space. We'll continue to use Z1, Z2, and Z3 to represent the coordinates of our ambient space. Our first challenge is to find a way to relate our surface coordinates S1 and S2 to our ambient coordinates Z1, Z2, and Z3. And we do that with parametric equations. So to show you how that works, let me put up a diagram of a simple curve that moves through space here. So we've got a curve with a point P, and we locate our point P, of course, with some sort of parameter. In this case, S, which is just the arc length along the curve. It's the distance from some arbitrary origin, typically the beginning here, along the curve. So for each point P on the curve, there's a unique corresponding value of S. All right, to relate our point P to the coordinates in the Euclidean space, we need parametric equations, and they look like this. We come up with three functions, Z1, Z2, and Z3. Each are functions of the value of S. So we find a point on the curve, find its corresponding value of S, plug that into the functions, evaluate the functions, and we come up with the coordinate values of Z1, Z2, and Z3. All right, you've seen this several times before, and there's really nothing unique about this relative to tensor calculus. You've probably done parametric equations before in other mathematical disciplines. What tensor calculus does bring to the table, though, is the ability to consolidate these equations into a single form. And by using a free index such as I, we're able to express all of these relationships concisely as a single tensor calculus expression like this. Okay, so what we're going to do now is to extend this idea for the use in surfaces. We're going to come up with parametric equations that look like this. Now they're very similar, but the difference is, of course, the number of arguments in our functions. Here we have a single argument of S. Here we have a list of two arguments. We have multivariable functions in this case. So what we do is we find a point in our surface. We find the corresponding unique combination of S1 and S2, the ordered pair S1 and S2. We take those values, substitute in each of the functions, and that gives us the ambient space coordinates of Z1, Z2, and Z3. And like the case of the curve, we can consolidate these expressions into a single expression that, again, uses a free index. And as it turns out, the form of this expression is exactly the same as that of the curve, because you'll remember in our tensor calculus syntax, the letter S here implies a list of all of the arguments in the particular space that we're dealing with. So what's interesting, and the genius of the tensor calculus syntax, is that the same expression works no matter what the number of dimensions are. Here we've got, if you think about it, essentially a one-dimensional submanifold embedded in a three-dimensional ambient space, and we use this expression to represent the parametric equations. Here we have a two-dimensional submanifold embedded in a three-dimensional ambient space, and it looks the same way. Now, the same equation would work in any case. For example, if we had a four-dimensional ambient space and we had a three-dimensional submanifold or hypersurface, the very same equation works. Now, you may have picked up on the fact that what we're doing here looks a lot like what we did back in video number 6. That's where we talked about coordinate transformations. If you'll remember, the expressions looked a lot like this back in video 6. We had something like this where the argument was, say, z prime. Well, uh, that's not coincidental because what we're doing here is really a coordinate transformation. We're transforming from the s coordinate system to the z coordinate system. So it's exactly the same technique. Now, there is a difference here, though, and that is that we cannot derive an inverse relationship. And that makes sense because not all of the points in our ambient space lie on the surface. So it's impossible to derive the s coordinates as a function of the z coordinates. So that's simply impossible. Otherwise, we do have a coordinate transformation here. All right, the next thing we need to do is to develop a way to represent vectors and tensors using our surface coordinates. And to do that, we'll apply the same techniques we used back in videos 8 and 9, and that's where we used a position vector to derive what we call basis vectors. Okay, now we do have one problem, and that is that we cannot establish a position vector using coordinates S1 and S2 on a curved surface like this. That's because a position vector only works in Euclidean spaces. However, since our surface is embedded in a Euclidean space, then we can make use of a position vector that originates in our Euclidean space or ambient space. So that's what we'll do. We'll have a position vector pointing to point P here. We'll call it vector R, as we have in the past. And it's a position vector that originates somewhere out here in the ambient space. Now, if you remember what these coordinate lines are, if we hold S2 constant and vary only S1, then our position vector is going to trace out this coordinate line. It's going to move along this line as the value of S1 changes, holding S2 constant. And of course, you'll remember that that means if we take the partial derivative of our position vector with respect to S1, we're going to get a vector that's tangent to this curve that extends out in a direction like that. Now, this will become what we call our S1 basis vector. All right, and if we take the partial derivative of our position vector with respect to S2, we're going to get a basis vector that goes out in this direction like this. So all we're doing is the very same operation we did back in videos 8 and 9. And it's simply this operation right here. We're taking the partial derivative of r with respect to each of our surface coordinates, and that gives us these two basis vectors. And of course, we can use our tensor calculus syntax to consolidate these into a single expression. We will have basis vector S alpha is defined as the partial derivative of our position vector with respect to coordinate S alpha. Okay, let me stop here for a minute and mention that you'll notice I used a Greek letter here for the index, and that's quite customary when we're dealing with surfaces, because when we're dealing with surfaces, the index values can only be 1 or 2. Now, the indexes for our ambient space can be 1, 2, or 3. So we'll distinguish the indexes here for surface usage as Greek letters. We'll continue to use I, J, and K for the indexes in the ambient space, but we'll use Greek letters for the indexes on our surface coordinates. Okay, now together these basis vectors, S alpha vectors, both of which are tangent to their corresponding coordinate lines here, will define for us what we have seen in the past video as the tangent plane. So the tangent plane is that plane that is tangent to our surface at point P. And since the basis vectors are tangent to the coordinate lines, then the basis vectors will lie in this tangent plane. And therefore, the basis vectors become a valid basis for any vectors or tensors that lie exclusively in the tangent plane. But what happens if we have a vector or tensor that doesn't lie in this tangent plane? Well, to accommodate vectors in general, we're going to need yet another basis vector, which we define this way. We'll have a vector that points perpendicular to the tangent plane, points upward in a direction like this, and we call this the normal. The normal is a vector that is perpendicular to both of our surface basis vectors and has a length of 1. It's a unit vector. Okay, so the way we define the normal is that we derive it based upon two properties. The normal has two very important properties. The first is that the normal is perpendicular to each of our surface basis vectors. So that means we have this relationship. The dot product of the normal with each of our basis vectors is going to be 0. They're orthogonal, or they are at right angles to each other. And the second property is that it's a unit vector. That means if we take the dot product of the normal with itself, we're going to get a value of 1. So we define the normal as the vector that has these properties. Now let me point out that the easiest way to derive the normal is simply to take the cross product of S1 and S2. That'll give us a vector in this direction. Then we divide it by its own magnitude to make it a unit vector. Now we could also derive a normal by taking the cross product of S2 with S1. If we did that, we'd get a normal that points downward. Now that normal would also have these properties. So the point is here there are two solutions for the normal, one pointing in this direction, one pointing in that direction. Either one works, and it's just a matter of preference which one to use. Pick the direction you want to work with, establish the normal, and then stick with it throughout the entire analysis. Now let me mention in passing that it is somewhat customary to pick what's known as the external normal. If you have a surface that is bounded into something like a sphere, then it is customary to choose the normal that points outward from the bounded surface. But that's just a matter of convention or preference. Now the normal as we've defined it here, taken together with our basis vectors S alpha, establish what we call the tangent space. And the tangent space gives us the framework we need to analyze vectors and tensors in general with respect to our surface coordinates S1 and S2. So with all of that having been said, I want to wind the video down by showing you what all of this looks like using specific examples. We'll start with a cylindrical surface of a fixed radius, and we will put a point on our surface, a point P that is restricted to the surface. And what we need to do next is to establish some surface coordinates, and we'll do that this way. We'll define coordinates theta and z as S1 and S2. Theta is the angle that's formed by this little door that swings here, and z is the vertical coordinate right here as the point moves up and down. It's the same as the coordinates we use in cylindrical polar coordinates, except there's no value of rho. The value of the radius is fixed. Okay, next thing we do is to set up some parametric equations, and we do that this way. So the parametric equations are a cosine theta, a sine theta, and z. These are the same coordinate transformations you'd see between cylindrical polar coordinates and Euclidean components of x, y, and z, except that there's no rho value. Rho is replaced with a constant of a. So x, y, and z are all functions of theta and z. And each time we move the point, you see that the ambient coordinates are displayed as you see here. Okay, next step is to show you the coordinate lines. The circle is what happens when we change the value of theta. The straight line is what happens when we move simply up and down. From these coordinate lines, we can establish the basis. the vectors S1 and S2 that are tangent to each coordinate line respectively. And those in turn will define the tangent plane that looks like this. And finally, we'll add the normal, which looks like this. And the two basis vectors plus the normal establish the tangent space that moves everywhere we move the point. And that's what it looks like for a surface of a cylinder. Okay, let's look at the next example, which is going to be that of a sphere. All right, so we go through the same exercise. We'll start by putting a point on our sphere. The point is restricted to the surface of this sphere of radius 4 units. So we establish, first of all, surface coordinates, and here we'll use the values of theta and phi defined the same way we define them for spherical polar coordinates. Theta is the angle from the pole down to the lower pole, the z-axis, and then phi is the angle of the little door that swings right or left. Okay, next step is to come up with parametric equations, and they're going to look like this. These expressions are the same transformations you'd see as those from spherical polar coordinates to Euclidean components, except that there's no value r. R is replaced by a constant value of a. So each of our coordinates x, y, and z are functions of theta and phi. Alright, so as I move the point, you'll see the ambient coordinates are calculated and displayed like this. Alright, next step is to show you the coordinate lines. As we change theta, we're moving along this great circle here. As we change phi, we're moving along this circle of latitude right here. Alright, that lets us then define the basis vectors S1 and S2 that are both tangent to the respective coordinate lines. And of course, you'll remember that the length of our basis vectors, when we take the partial derivative of a position vector that is associated with a circle, then the length of our basis vector is going to be equal to the radius of the circle. Alright, so those two vectors then will define the tangent plane that looks like this, and finally the normal is this. We're using the external normal that points outward from the bounded surface, and so that tangent space follows the point wherever we go. And that's how it works for a sphere. Okay, one final example, and that's the surface known as a torus. A torus is a surface that looks like a donut, and it is characterized by two values. First of all, there's the actual radius of the donut itself, which we will represent by the letter A. I think I have it set to a value of 4 right now. And then the second property is the radius of the circle formed by the cross section right here. That's the radius of the actual tube itself, and we'll represent that with the letter B, and I think I've set that now to a value of 1.5. So to work with the torus, we first of all place a point on it like this, and we can move the point around the surface as we did with the other surfaces. So next we'll establish some surface coordinates, and for those we'll use the values of theta and phi. Now to see what's going on here a little bit better, let me take off the surface for a minute so you can see what's going on behind the scenes. Theta is the angle formed between this segment on the xy plane and the x-axis. So as I change theta, it swings the segment around like this. Now, phi is the angle formed around the circle that is in a plane that is perpendicular to the xy plane. So as I vary phi, then it swings around up to 360 degrees in this direction. So between the two, we vary theta and phi. We'll sweep out all the points on the surface of the torus. Okay, next thing is to establish a set of parametric equations, and they'll look like this. Now the value here in the parentheses, a plus b cosine phi, is just the distance from the origin all the way out to the point along the xy plane here. So we have a plus b cosine phi brings us out to this point. So that'll be the distance that p is from the z-axis. And of course, we add cosine theta and sine theta to develop the projections of the point back to the xz plane and the yz plane respectively. And then the height of P above the xy axis is simply the radius of this smaller circle times the sine of phi. So that's how we come up with the parametric equations for a torus. Okay, let me put the surface back in place here. Alright, so you can see how the values change as we vary theta, first of all, and phi. Okay, so now we're in a position to display the coordinate lines. So if we change theta, it moves along this coordinate line. If we change phi, it moves along this coordinate line. All right, from there we can display the basis vectors. Again, they are tangent to each of the coordinate lines respectively. That will give us the tangent plane, and we can add the normal to define the tangent space. And as with the other surfaces, the tangent space follows wherever the point goes. All right. That's how it works for a torus. All right, so I think you get the idea now. So we'll end the video with a short recap. The first thing we did was to show how we can use this one simple expression to develop a parametric description for our surfaces. Now, as the free index indicates here, we have one function for each of the coordinates in our ambient space, and the argument of each of the functions is a list of the surface coordinates. What we have in effect here is a coordinate transformation where we're transforming from our surface coordinates to the ambient coordinates like this. It works just like it did back in video 6 for coordinate transformations. However, the difference is that we cannot establish an inverse transformation. It's only a one-way transformation from surface coordinates to ambient coordinates. All right, the next thing we did was to define surface covariant basis vectors. And we did it the same way we defined basis vectors back in video 9. We take the partial derivative of our position vector with respect to each of our surface coordinates, and that establishes the surface covariant basis vectors. Now these vectors act as a basis for any vector or tensor that exists exclusively in the tangent plane. But we then went on to define what we call the normal, which is a vector with these two properties. The first property is that the normal is perpendicular to each of our basis vectors, so the dot product with each basis vector is going to be equal to 0. And the other property is the dot product of the normal with itself is equal to 1. That's because it's a unit vector. And we pointed out that there are two orientations in which the normal can be defined. It can either point upward or downward. Typically the convention is that if we have a bounded surface, we'll use what we call the external normal, the one that points outward from the bounded surface. But it is a matter of preference. You can use either one, and everything works properly. Just pick the orientation of the normal that you prefer and stick with it throughout the entire analysis, and everything will work out just fine. And finally, we said that our basis vectors here, combined with the normal defined here, define and establish what we call the tangent space. And that's a space that lets us analyze any vector or tensor with respect to our surface coordinates. So let me end with one final comment that may already be obvious. I'm going to be developing everything along the way for two-dimensional surfaces that are embedded in three-dimensional Euclidean ambient spaces. However, the results are going to be general in nature. We're going to develop them in such a way that everything we do is going to apply to submanifolds of any size. For example, in these equations, if we had a four-dimensional ambient space, we'd have four functions. And in each of those cases, we'd have three coordinates to our hypersurface. And then in this equation, we'd be defining a set of three surface basis vectors. And those three vectors combined with the normal would give us the tangent space. So the normal would be a vector that is perpendicular to each of the three basis vectors and is a unit vector. And those four vectors together will give us the tangent space. So just keep that in mind as we go. I'm going to develop it as if it's a two-dimensional surface, but you can just know each time that the results are quite general and can be applied to any abstract level.